Hi, I'm Ataberk, and today I will present QUAC-TRNG. I'll start with a high-level summary of our work. DRAM-based true random number generators can provide low-cost true random number generation to a variety of computing systems. However, prior DRAM-based TRNGs cannot provide low latency and high-throughput true random number generation, as these TRNGs either sample fundamentally slow physical processes or cannot effectively harness entropy from DRAM rows. Our goal is to develop a high throughput and low latency TRNG that can be implemented using commodity DRAM devices. We make the key observation that a carefully engineered sequence of standard DRAM commands can activate 4 consecutive DRAM rows in quick succession. We call this new phenomenon quadruple activation, or QUAC for short. Our key idea is to use QUAC operations to simultaneously activate DRAM rows that contain conflicting data to generate random values on DRAM sense amplifiers. We develop QUAC-TRNG, which repeatedly performs QUAC operations and post-processes the results using a cryptographic hash function to generate true random numbers at high throughput and with low latency. We evaluate QUAC-TRNG's throughput and quality using 136 real DDR4 chips from 17 DDR4 modules. Our results show that QUAC-TRNG can achieve up to 5.4 gigabits per second throughput per DRAM channel, outperforming the state-of-the-art by 15 times for base and 1.4 times for throughput-optimized configurations. We show that QUAC-TRNG generates true random numbers with low latency. We use the standard randomness tests developed by the National Institute of Standards and Technology to measure the quality of QUAC-TRNG, and we show that QUAC-TRNG is a high-quality true random number generator. High-quality true random numbers are critical to many applications. These applications include cryptography, scientific simulations, and machine learning. True random numbers can only be obtained by sampling random physical processes, and unfortunately, not all computing systems are equipped with dedicated TRNG hardware. DRAM is commonly used as main memory in a wide range of computing systems. TRNG is based on DRAM enable low-cost and high-throughput true random number generation within DRAM chips. DRAM-based TRNGs do not require additional specialized hardware for true random number generation. Therefore, they're beneficial in constrained systems. DRAM-based TRNGs open application space in systems that require high throughput true random number generation. DRAM-based TRNGs are also synergistic with processing in memory systems. These systems perform computation directly within memory and improve system performance by avoiding inefficient off-chip data movement. DRAM-based TRNGs enable pin workloads to sample true random numbers directly within the memory chip and improve the overall security and privacy of these systems by avoiding communication to possible off-chip TRNG sources. The problem with existing DRAM-based TRNGs is that they're slow. A subset of these TRNGs sample fundamentally slow physical processes, such as DRAM charge leakage. Other DRAM-based TRNGs cannot effectively harness the available entropy from DRAM rows. Our goal is to develop a high throughput and low latency TRNG that can be implemented using commodity DRAM devices and requires no additional specialized hardware for true random number generation. We make a key observation. We see that a carefully engineered DRAM command sequence can activate 4 DRAM rows in real DRAM chips. We call this phenomenon quadruple activation, and we refer to it as QUAC. Our key idea in developing a high-throughput DRAM-based TRNG is to use these QUAC operations and activate DRAM rows that are initialized with conflicting data to generate random values on DRAM sense amplifiers. I'll quickly describe how we use QUAC to generate random values on many sense amplifiers. Here are 4 rows of DRAM cells. A DRAM cell looks like this. It stores data as charge in a capacitor, and it's accessed over an access transistor, which is enabled by a DRAM word line. A row of DRAM cells share a common word line. DRAM cells on different DRAM rows share the same bit line that's connected to a sense amplifier. These sense amplifiers amplify the deviations in bit line voltage to an IO-readable value when a cell is accessed. We initialize these DRAM rows with conflicting data patterns. The odd address rows are filled with all ones and colored gray, and the even address rows are filled with all zeros and colored white. When we perform a QUAC operation, all 4 rows become activated, and consequently, 4 cells on the same bit line start sharing their charge with the bit lines. To do so, we send an activate precharge activate command sequence with violated timing parameters. We hypothesize that this keeps the bit line voltage below a reliable sensing threshold, and some sense amplifiers cannot correctly amplify the bit line voltage. Then, these sense amplifiers randomly amplify the voltage either to a logic 1 value or a logic 0 value based on noise originating from random physical processes. We develop QUAC-TRNG, which generates true random numbers at high throughput by exploiting this behavior. We first measure the randomness on bit streams generated by repeatedly performing QUAC operations on DRAM sense amplifiers. We use Shannon entropy as a measure of randomness. The intuition here is that sense amplifiers that generate a constant stream of either logic 0 or logic 1 values will have 0 Shannon entropy, whereas sense amplifiers that generate bit streams with an equal amount of 1s and 0s will have 1 Shannon entropy. Following the one-time characterization step, we identify arbitrarily sized contiguous data blocks in sense amplifiers, each with a collective 256 bits of Shannon entropy. QUAC-TRNG will read each such block to produce a 256-bit true random number. Overall, one QUAC-TRNG iteration looks like this. QUAC-TRNG initializes the 4 DRAM rows that are activated together and performs a QUAC operation on these 4 rows as I described in the previous slide. It then reads these blocks to the memory controller and post-processes each block using the SHA-256 cryptographic hash function to finally produce a 256-bit true random number. We conduct a characterization study on 136 real DDR4 chips from SK Hynix to both understand the randomness characteristics of values produced by QUAC operations, such as spatial distribution and data pattern dependency of entropy, and to evaluate QUAC-TRNG. We use a modified version of SoftMC, a DDR4 memory testing platform that lets us issue arbitrary DDR4 command sequences with any set of timing parameters to DRAM modules. We use rubber heaters and a temperature controller to maintain the temperature of the DRAM chips at 50 degrees Celsius during our experiments. We observe that QUAC-TRNG provides true random numbers at up to 5.4 gigabits per second throughput, outperforming the state-of-the-art for their base versions by 15 times and their enhanced or throughput-optimized versions by 1.4 times. QUAC-TRNG also provides true random numbers with very low latency. We evaluate random bit streams generated using QUAC-TRNG and show that they pass all 15 standard randomness tests. We evaluate QUAC-TRNG's area and memory overheads. Including the accelerator for the cryptographic hash function, QUAC-TRNG introduces negligible area and memory cost. We observe that QUAC-TRNG is sensitive against temperature changes, and we see that time elapsed on the order of a month does not have a significant effect on QUAC-TRNG's quality. Thank you for your attention. I invite you to watch our full talk and read our paper for more detail.